systems. And so the next talk will be given by Nathan Wiebe, who's going to tell us about ways you can use quantum computers to understand properties of quantum systems.
Thanks a lot, Andrew. So yeah, I'm really excited to be here and get a chance to talk to you guys about, probably what I'm most excited about in quantum computing, which is simulating physical systems. And so I think this is going to hopefully will be a very useful talk because, well, later on today we've got Ryan talking about quantum simulation algorithms for chemistry. A lot of the methods that he's going to be talking about will be directly using the ideas that I'm presenting here. So it's at least my hope that it'll make many of the ideas that he presents in that second talk much clearer. Also, because we've got a relatively small audience, feel free to interrupt me at any time. I really would rather, people in the audience get something out of this talk rather than necessarily get exposed to all ideas at a level of detail that I thought, according to my prior, would be reasonable. So, great. So just to give you an idea about what I'm hoping to talk about here, the main point that I want to discuss is I really want to give you an idea about what are the sorts of things that people have been thinking about and exploring over the last couple of years in quantum simulation. And in particular, I'm going to be talking about three main techniques that I think are very important for people to have at least heard about in quantum simulation. The first and most and easiest of these is trotter-based methods for quantum simulation, then linear combinations of unitaries methods, and finally, qubitization. These names will make a little bit more sense. I can't guarantee they'll make 100% sense, but they'll make a little bit more sense by the time I make it to the end. But one of the first things that's going to be very important, especially in the context of the last talk, is to really clearly discuss what we mean by quantum simulation. Many of us come from different communities, and many of us use the term quantum simulation and have a very strong view about what this ends up meaning. And each field, I find, uses it differently. So the view I'm going to be using for quantum simulation is often going to be the view that quantum computer scientists often take for simulation. So as opposed to looking at static properties, which people usually look at in DMRG, tensor networks, things like this, the primary focus is going to be on dynamics. Because curiously, dynamics are the more natural thing to simulate on a quantum computer for most algorithms than statics. So just to give you an idea, why do we care about quantum simulation? Well, all right, I resisted the temptation to give the standard Feynman slide here, but quantum simulation really was sort of the first natural application of quantum computing. In fact, in many ways, it sort of is the natural application for it, because if you think about it, what does it mean to have a universal quantum computer? A universal quantum computer is a device that's capable of performing any unitary transformation on a set of qubits. That's it, or at least approximating it. And so if you look at what quantum physics describes for the dynamics of quantum states, it describes dynamics as a unitary evolution on a quantum state. So then the task of simulating a system is really just a task of compiling that unitary that nature gives you down to a set of gate operations. Okay, great. So now all of you understand quantum simulation. So any questions? Yeah.
Very much. That actually that unitary is just part of it. The other part is that it's local. So it is very important that in a quantum circuit you compose your unitary from local gates and not just arbitrary unitary.
Sure. I mean, one of the issues that this is a good point that I'm going to yes, there are slides after this. Don't worry. The question about what the input model is and what the assumptions are in the Hamiltonian are going to be quite important. At some point, if you're interested in doing this on a physical quantum computer, you are going to have to worry about local interactions. However, in the model that I'm discussing here, I'm not going to go into detail about how to do this precisely in terms of local operations, but that's a good point. So basically, that's the idea, is that we really want to be able to compile quantum dynamics into a sequence of gates that can be run on a quantum computer, ideally local gates. And so this to me, I think is really neat, because if we look at algorithms like Shor's algorithm, that provides you a speedup for precisely one class of problems. Quantum simulation, it's an entire toolbox. There's a host of different problems that we can solve with this. Not just the standard ones, answering questions about catalysis, probing the question about what the mechanisms are behind high temperature superconductivity. But also, these techniques have been used in a host of other places, such as quantum machine learning algorithms, algorithms for preparing Gibbs states. So it actually really is a fundamental tool that appears in a bunch of quantum algorithms, and not necessarily just in its raw application. So the form of Hamiltonian simulation I'm going to be taking a look at mostly, again, is dynamical simulation. So this, unfortunately, doesn't display all that well, so I'll have to pantomime a bit. But basically, the idea is that imagine you've got a physical system. You're provided as input some initial state. Now, that initial state is going to evolve according to a time evolution operator, e to the minus iht. And it evolves through some trajectory down to some final state over there. And so what we want to do is we want to be able to map this to a quantum computer. So there's several steps in this. The first one, we take the initial state and we just find some encoding to map that to a quantum bit string in the quantum computer. Note this quantum computer I've drawn is bigger than the physical system, and that's often because we need ancilla qubits to represent it. So formally, the Hilbert space that describes the quantum computer is often bigger than the Hilbert space of the physical system we're trying to simulate, just because of overheads. But anyways, we begin by encoding that quantum state in the quantum computer up to some error. Then what we do is we do a series of gate operations that takes it to some other place in the Hilbert space. Then what we hope is if we've done our compilation properly, this final quantum state in the system should be logically equivalent to some state that's within distance epsilon of the target state, for an epsilon that you propose before the algorithm starts. So ideally, you don't want that epsilon to be 1. You want this to be something that's programmable and controllable. And what you'd like to do is you'd like to have algorithms that, for every epsilon greater than 0, can give you a complexity of getting that state within distance epsilon. So that's the dynamical simulation problem that we're interested in looking at here. There's a number of things, though, that end up coming in. First is, well, OK, how exactly do we do this compilation process to map this across? Obviously, this curved line doesn't give you much insight on how that would actually be done. And there's a bunch of techniques for doing it. But there's another couple of points that I'm going to spend differing degrees of discussion on. The part of the discussion that I'm going to spend almost no time on is discussing how we prepare this initial state psi of 0 into it. This problem is vitally important for applications like quantum chemistry, but typically when computer scientists end up looking at this, they just take this as a given, like it's some input to the problem. All right? And as for the output is formally a quantum state. But in general, we don't want just a quantum state, because a quantum state doesn't provide any information in and of itself. Normally, we'd like to learn things about the quantum states. And so the idea basically is that often this primitive algorithm in here for quantum dynamical simulation is just a box that's going to be running inside a larger quantum algorithm to give you estimates of the things that you're actually interested in. All right? So that's basically how it all goes. And yeah, so formally, we want to be able to, say, minimize for this problem, the norm of the difference between the evolution in that. And of course, for all the methods that we consider for doing this compilation, we'd like to pick the one that's cheapest. So as for the input for this, now what I mean by the input here is I don't mean the initial state. I really mean if we've got some black box algorithm that's capable of simulating Hamiltonian dynamics in general, it'd best know what the Hamiltonian is. If it doesn't know what the Hamiltonian is, there's something deeply wrong with your algorithm. So there's a bunch of different models that you can use for it. One of the easiest ones, I think conceptually, is this model I called, I don't think it's got a name formally, but I'm going to call it unitary access here. And what the idea basically is assume your Hamiltonian is a sum of a bunch of different unitary matrices, where these AJs are just some coefficients. So you might think, all right, this doesn't sound all that natural. When do you have a decomposition into a sum of unitaries? Well, it turns out Pauli operators are unitary. So actually, most physics models that we use to describe nature take this form up here, at least in the most convenient way for us to represent it. Barring that, what we can do is we can take a general Hamiltonian and decompose it into a sum of unitary matrices in general. But I'll discuss that later with the next access model in more detail. So all right, this is the specification of the problem. We've got a sum of unitaries that comprise the Hamiltonian. What we need to be able to do is we need to be able to apply these and compute their weights. So
I just can't read that equation. J psi equals J H J psi. What does that mean?
okay, so let me just explain then what this means.
Just say, because I can't.
Yeah. That's what I want to say. So basically, what the select thing does. Yeah, what that unitary does is it takes an index j, which says which unitary is it, and then it applies that unitary to the quantum state you want to simulate. So think about it as a programmable applicator, so to speak, that ends up.
So that's a computer. That's a programming call, not a mathing.
Yeah. So so in any case, what the idea basically is it applies the unitary in question to it. So this just allows you to say, for any unitary, let's programmably apply that one unitary to the quantum system. But that doesn't give you the AJs, right? That only gives you a way of applying the HJs. The way that the AJs are accessed is through this prepare circuit, which is a unitary that prepares the coefficients in a quantum superposition over there. And so these two elements give you everything that you need in order to be able to simulate dynamics in this context. And it's very nice to use in cases where you're simulating physical systems, but this model isn't actually so convenient for more broad applications. A more broad approach that is used, and actually was popular before this top one, is an approach that I call the sparse matrix access model. And so the idea basically is, all right, assume your matrix doesn't have any known structure a priori. Nobody gives it to you as a sum of unitary matrices. But what they tell you beforehand is that the matrix is d-sparse, meaning that there's at most d non-zero matrix elements in every row and column. And also, assume that the sparsity pattern is computable. So there's an efficient function that you can run that'll tell you where exactly these potentially non-zero matrix elements are located in every row. And so how the access model works is it gives you quantum circuits, or black boxes, that give you a representation of that function, which says where is the non-zero matrix elements, and another function which tells you what its value is. Sometimes people combine them together into one kind of super black box, but I prefer to separate them. So that's the basic idea behind it. And the final one, which I'm not going to really be dealing with much at all, mainly because I don't like it, is density matrix access. So in this model, what happens is that the Hamiltonian is literally given to you by a potentially non-unitary source that gives you a density matrix. And the idea basically is a density matrix is a Hermitian operator. So actually, that is effectively a Hamiltonian. And so if you've got that sort of access, then you can implement e to the minus I rho t. So this gives you a way that you can simulate dense Hermitian matrices in this fashion. And it works okay if you've got low rank, but in general, this method is really, really costly. So I don't care for it. But it's commonly used in quantum machine learning. So it's worth knowing about at the very least. All right, so then now, yeah?
Your original formulation was that this is time evolution?
Right.
So I'm trying to understand this unitary access. There's no time in there?
Okay, so there's no time in there. So let me try this again. All that I'm doing, trying to describe in these, is just describing formally what subroutines provide the algorithms with the values of the matrix elements of the Hamiltonian. And so
I'm trying to think of this as being useful as it's going to be used. We're going to freeze time for a little bit and do something there. But I'm just trying to understand this unitary gate. This is a unit. Sorry, are you on that top line? Are you decomposing the Hamiltonian or e to the IH?
No, this is the Hamiltonian that's being decomposed. Yeah. So in all of these cases, it's the Hamiltonian that's being written in different forms. And yeah. Okay, great. No problem at all. Any other questions?
Yeah, can I?
Yeah.
I'm going to take advantage of Umesh's comment at the beginning of asking stupid questions. We have a very different audience here. I mean, do you know that every unitary can be unitary equivalent to a sparse matrix with 5 diagonals at most. As long as you have one cyclic vector. This is the general theory.
Oh, I didn't know that.
Your condition there seems to be okay.
So,
Doing it in practice may be hard.
Yeah.
That's another story.
well, normally in general, what's used is, at least the standard method that was used for decomposing this for the second approach, is that graph coloring techniques would be used in order to write the Hamiltonian as a sum of one sparse matrices. Now, one sparse Hermitian matrices are also unitary, so that's something that's also kind of nice about it. So the only drawback of these methods is that they tended to require a large number of matrices in a decomposition if you wanted to do this efficiently. But I'd love to hear about other methods that could be used for this because, yeah.
I mean, these are called CMV matrices, and they play a very important role in mathematics. Maybe everyone knows about them, maybe not.
I didn't, so, great, thanks. So these are basically how you get the Hamiltonian in. As for the output, really there's a couple of things that we want usually to get out of this. The first is we'll often want eigenvalues. We'll want to know spectral information about this. So the idea behind this is that what you do is you use the quantum simulation methods that I'm going to talk about to represent a unitary, and you plug that into a phase estimation circuit. And that phase estimation circuit will give you a way of estimating the eigenvalues. Sometimes you'd like to be able to learn the expectation values of observables. Normally the way that you'll want to do that is you'll set up some circuit, like a Hadamard test or something like that, that will be able to give you indirectly the expectation value of that observable. And then you just run an algorithm like amplitude estimation on top of it in order to be able to figure out that expectation value inexpensively. A final one that often is that people often will use is they'll want to know the distance between different quantum states. And the easiest way to do that is to apply this standard circuit called the swap test. So for the output, there's a bunch of things that you can end up doing after you get the quantum state back out in order to be able to extract things of physical meaning. So let me talk about the first method for a compilation. This is perhaps at least from a physicist's perspective, is the most natural way to simulate Hamiltonian dynamics. And this is Trotter-Suzuki methods. And so the basic idea is that imagine we've got Hamiltonian that's a sum of these terms over here, and I don't need to make any assumptions about the unitarity here. But in any case, the basic idea behind this is that what you do is you say, all right, the time evolution operator is the exponential of the sum of all of these individual terms. Now, if all of these terms commuted, then what I'd be able to do is I'd be able to say, oh, well, I can express the exponential of the sum as a product of each of these individual terms. Now, if each of those HJs is simple, like say a Pauli operator, then we can design easy circuits to handle each and every one of those guys. And then that's how we do the simulation. Now, in practice, of course, they don't commute. So there's errors that end up coming in, and that's what these errors over here represent. And so then the tactic behind Trotter-Suzuki formulas is what you do is use a stroboscopic approach for simulation. What you do is you break up your time evolution into a series of R time slices, and by making R shorter and shorter and shorter, you can make those commutator errors smaller and smaller and smaller, and eventually end up making the error 0. So that's the idea behind it. You take your Hamiltonian as a sum of easy terms over here that you know how to individually simulate, and then use the Trotter-Suzuki decomposition in order to break it up into a sequence of those easy to simulate terms, rather than an exponential of the sum that you wouldn't know how to do directly. All right? And so basically, the idea is that if you look at the simplest formula for this, you end up finding that it ends up scaling like 1 over r. So you need a number of slices that would scale quadratically with the evolution time, which it'll work, but it really sucks, to be honest. So you can get around this by using higher order formula over here, which can be recursively derived from the symmetric form of that. And this sucks less, but it's still not devoid of suck. So the point is that when we end up using this, what we end up getting is a complexity that scales by optimizing the value of k that we have for this. We end up getting something that scales superlinearly with the evolution time t. Right? Now the problem is that the actual limit, the fundamental limit that you can end up getting for this is linear in t. So there's a subpolynomial, but not polylogarithmic bit of this over here that is left over. And so these methods, formally speaking, are not optimal, which is a drawback. Another problem is that the error bounds that we can end up proving for these formulas they're concise, they're easy to use, but they really blow. So to give you an idea about how awful these error bounds are, these are some of the best error bounds that I knew of when we did the nitrogenase simulation paper. Up here, these are the values that we computed using upper bounds on the error in a Trotter-Suzuki formula for the complexity of simulation. And these are numerical results using the exact values. They're loose by a factor of about 10,000. And so, and bear in mind, at least at the time, those were the best known bounds that were available. Yeah?
This fundamental limit that you said, we cannot do anything sublinear in T, so that's based on what?
Okay, so what that's based on is a Hamiltonian that can be used in order to compute parity. So what you do is you design this Hamiltonian that could compute parity, and you show that if you were able to simulate this evolution of the Hamiltonian faster than linear in T, then what would happen is you'd be able to, with fewer queries than you require in order to solve the parity problem, you'd be able to solve it. So it's a proof by contradiction.
So it's an information theoretical.
But also, it would be very surprising in general if you could get, polynomial. Yeah. So, okay, that's one of the things that is hard about it. One of the things, though, that is, I think, actually really kind of neat, though, about these Trotter-Suzuki formulas, is that the error ends up varying with the commutators, not the size of the Hamiltonian. So, for example, if all the terms in a Hamiltonian commute, there is no error in a Trotter-Suzuki decomposition, and it becomes a stupidly efficient method for simulation. Whereas the other methods that I'm going to be talking about don't have this property. So that's one of the reasons why Trotter-Suzuki formulas, intuitively, despite the fact that the error bounds are awful, actually might be pretty awesome. And so the other things that I should mention is that similar bounds for the fourth order formulas for local Hamiltonians have been shown. To this general one for the second or third order formula, depending on how you count. And also another thing that's quite interesting about it is this recent result that Andrew and some other people worked on, which addresses the question of how you should order terms in your Trotter-Suzuki decomposition. And so intuitively, it might seem that if you randomize between every one of your steps the ordering of the terms, then the errors may cancel out in some advantageous way. And well, people had looked at this informally in the past. This result ends up showing that in some circumstances, you can actually do quadratically better in terms of your scaling by randomization. So that's a pretty cool result, I think, and shows that really, even though Trotter-Suzuki seems like it's in some ways it's suboptimal, there's a lot of gas left in this tank.
What was that formula at the bottom actually for?
So what that formula at the bottom is for is, I believe, the number of gates that are required for the simulation. All right. So now let me talk about linear combinations of unitaries methods in the increasingly shortening amount of time that I've got. So the idea basically is that, let's say you want to do a simulation, you don't know about Trotter formulas. What's the dumbest thing that you could possibly consider to do? You might say, oh, I know. What I'm going to do is I'm going to just write out the Taylor series for e to the minus iht and implement that on a quantum computer, right? How hard could that be? Well, there's one minor problem with that, and the problem is that if you truncate the Taylor series at finite order, it's not a unitary. And since quantum computers naturally do unitaries, how do you do this? Well, turns out there's a gadget for doing this that looks like this. And basically, the probability of success ends up scaling like 1 over this sum over here. And by choosing the one norm of these coefficients times t to be equal to log 2, you can make the probability of success anything you want. And if you can make a probability of success anything you want, the answer is always 1/4. Okay, you might want 1, but 1/4 is the next best thing. The reason why is because at 1/4, you can use amplitude amplification to boost that probability of success to 100% with one iteration. And so that's the basic idea behind this method. You use this non-deterministic gadget to implement the sum of those unitary matrices. You choose the evolution time in each segment of it to satisfy this probability of success approximately 1/4, and then you use amplitude amplification to boost it the rest of the way. And that's how these methods end up working. So in many ways, its complexity is much nicer than Trotter-Suzuki. It ends up scaling linearly, well, near linearly with t, and it ends up scaling logarithmically as opposed to subpolynomially with 1/epsilon. And that's something that's really awesome. But another thing that's great is that you can also simulate time-dependent evolution with this. So if your Hamiltonian is explicitly time-dependent, you can also do it using this formalism. So, but something that's very neat about this is because of the fact that what you can do is you can slice up the evolution into a sum of different unitaries and then use an exponential superposition over those unitaries, you can give yourself effectively an exponential number of time steps in that superposition that you're doing in a single step. And that gives you a fast way of kind of doing a Monte Carlo approximation to this unitary up at the top over there. And because you have this ability to do an exponential number of time steps essentially with this, that ends up giving you a complexity that in the end only scales logarithmically with the maximum derivative. In contrast, if you were to try to do the same thing with Trotter formulas, it would scale like the square root of this.
Can I ask another dumb question? I mean, you write u of t on the left-hand side.
Yeah.
That means unitary?
That means unitary. It means e to the minus iht.
Why is that h has been taken to be unitary itself and not self-adjoint?
Okay, h is not unitary. H was given as a sum of unitaries. So h...
Why don't you take it as a sum of self-adjoints?
I could. But for some of these methods, what I would need to do, if I just took it, the most extreme cases, I could take it to be itself. Right? And then I would still need some method in order to decompose the problem, the simulation problem, into a sequence of simple simulation problems that I can then compile onto a quantum computer. And so I would still need to do, in some ways, a decomposition of the Hamiltonian into simpler objects with this. So for these methods over here, for the linear combinations of unitaries, I'd have to choose some class of elementary unitaries to decompose them into. For other methods, I wouldn't need to do that, but for this one, I would. Okay. And I should mention, I said e to the minus iht here. That's formally not true. I mean the time evolution operator, because this is for a time-dependent Hamiltonian.
I'm just trying to help you. It's a very clever thing they've done. The Hamiltonian is self-adjoint to Hermitian, but by writing it as a sum of unitaries, it enables his methodology. It's cleverness. It's in the service of his methodology.
But I mean, this formula there, ut equal to that sum, works if h is self-adjoint. Otherwise,
no, it's self-adjoint, but he's trying to he has a technique for simulation which is enabled by writing the Hamiltonian as a sum of unitaries. That helps.
And so yeah, that's exactly it. So yeah, you just want to do this because the problem of simulation is a compilation problem. What we want to do is we want to take some complicated dynamics, break it up into a sequence of simpler problems that we know how to solve. And all of those, at some level, involve applying a unitary. So it's just a question of where you want to draw that line, really.
Sorry, can I ask you, so, I'm not sure I fully appreciated the complexity of the prepare select step, so in terms of the access to the Hamiltonian. So can you say a word about that?
Okay, so the complexity of the prepare and select, you see, that depends very strongly on the particular case that you're looking at. So in general, the cost of doing the prepare, because there's m coefficients you've got to put in, obviously if there's no structure whatsoever to those, the complexity of that has to be polynomial in m, right? But what the deal is that, and with select in general, the worst case is if you've got no structure, you have to have just one control for every single possible term in the Hamiltonian. But often with the sorts of circuits that we end up looking at, there's a lot of structure to that. So we find that often the cost typically will be much less than that. But yeah, in general, the cost is going to be polynomial in a number of terms in a Hamiltonian. But the key point is with this over here is because the Hamiltonian evaluated each of these individual times, it has a lot of structure between it. What you can often end up doing is you can use this structure in order to reduce the number, the complexity of that query. So it becomes actually logarithmic in the number of time steps that you end up using here rather than polynomial. So this ends up leading to this new result that we're happy about, but I'm nearly out of time, so I'll just skim through it really quick. Basic idea is that because for some of these methods with linear combinations of unitaries, the cost of in terms of the derivatives is logarithmic rather than linear, what you can do is you can use this transformation to an interaction picture in order to take big terms from the Hamiltonian and switch them into the derivatives of a time-dependent Hamiltonian that simulates a time-independent Hamiltonian. And so by doing this, what we can do is we can reduce the cost of simulating diagonally dominant Hamiltonians dramatically, in some cases exponentially. So that's basically the idea. Here's some theorems that I don't have time to talk about. OK, qubitization, final thing, which I also don't have time to talk about. Basically, the idea behind qubitization is to take a quantum walk whose eigenvalues are that are related to the eigenvalues of the Hamiltonian that you want to simulate. Then this quantum walk operator is defined in terms of a reflection times the select operation that I talked about. And so when you go through that, you end up finding that basically the eigenvalues of this over here in each two-dimensional subspace that this walk operator acts on ends up being just the arc cosine of the eigenvalues times a sigma y operator. And so when you expand this all the way out, you can see that this ends up simulating e to the I arc cos of the Hamiltonian, basically. Then, basically, the rest of this technique just involves going through and using this technique in order to remap the eigenvalues using a polynomial transformation into the eigenvalues of the real one, because you do want to get rid of that arc cos. And this formula over here allows you to introduce a bunch of Bessel functions and a Fourier series, essentially, that will end up implementing that.
Sorry, this was kind of fast. So.
Yeah, sorry about that. I ran out of time. Yeah. Oh, we got time, Andrew?
Yeah, I think we can be a little flexible.
All right, cool. Well, thank you for pulling me back then.
Even one more slide.
All right, cool.
One more. Where's the first slide?
OK.
Oh, yeah.
Okay. So this wall of text. All right. So let me try again with my now empowered time budget. So basically, what the idea is that in this context, what we want to do is we really want to. This boils down to a lot of intuition that Andrew had in one of his earlier papers, which is the fact that quantum walks are equivalent to Hamiltonian simulation. So the idea is that for one part of that proof, what you need to show is you need to show that for every Hamiltonian, there ends up existing a quantum walk for it. And so one way you can end up doing this is by constructing a walk operator, W as I call it over here, which ends up basically being equivalent up to an isometry to the original Hamiltonian that you want to simulate. And this, the way that this walk ends up working is it involves a reflection about this state L. And this state L over here is really just that state that I talked about that encodes the amplitudes of the various terms in the Hamiltonian. And select, what it does is it really just applies HL to each of those. Now, if each of these HLs is unitary and Hermitian, then this also is a reflection operator. So that basically is the idea behind it. So we apply this over here, and it may, at first glance, seem totally unobvious how this has any connection whatsoever to Hamiltonian simulation. And the connection really ends up coming in this matrix that I was describing over here. What you can, for walks of this form, the walk operation boils down to a sum over two-dimensional irreducible subspaces. Okay? So in order to diagonalize the walk operator, it suffices to look at each of these individual subspaces. And this is an example of what one of those subspaces ends up looking like when you rip it away. So these EKs over here are the eigenvalues of the Hamiltonian. Lambda is if you recall over here, is defined to be just the sum of the, in general, absolute values of each of these coefficients of the Hamiltonian. And so you can see, hey, wait a second, that looks just like a sigma y rotation. And so that's what I wrote over here. This is just the sigma y rotation that is equivalent to that two-dimensional matrix over there when you break it up into these little blocks. Okay? So you can see, yeah.
The blocks, how did you define them again?
So the blocks over here, the way that, that I end up defining them is I say, okay, let's take a look at the action of W on one of the eigenvectors of it. So I want to be able to take an eigenvector of H and see what space it ends up mapping that onto. So that forms an irreducible two-dimensional space in it, and that irreducible two-dimensional space can be mapped as this.
So the top left corner has overlap on L, and the other guys, they're just outside?
Yeah, they're mapping to the state orthogonal in that two-dimensional space to it. So yeah, exactly. So
Make sure that's all for analysis, so you don't actually compute these things.
no, this is all for analysis. This is just to give you an idea about how you can construct this walk operator, which then gives you a method to do the Hamiltonian simulation. Right. So the idea basically is that you can see that this has exactly the same eigenvalues, well, plus minus because of the eigenvalues of y, but it's got the exact same eigenvalues as the original Hamiltonian, but arc-cosed and renormalized. So if you've had a way to undo the arc cosine, then you'd be able to turn this into a general purpose simulation method. Now, the original method that was proposed to do this was phase estimation. So if you just applied phase estimation to this, you could learn the eigenvalues coherently, and then you'd be able to invert using ideas like the Harrow-Hasselman-Lloyd algorithm. But there's a slicker approach that can be used, and that's this Jacobi-Unger formula over here. And basically what that, as I said, ends up doing is it ends up allowing you to get rid of or introduce an arc a sign up at the top as a sum of this. And so by doing that and putting in a phase shift on it, you can get a cosine which ends up inverting the arc cosine and gives you exactly the evolution that you want. So this formula, coupled with either linear combinations of unitaries or this technique called quantum signal processing that Guang Hao and others invented, give you a method for doing this. And so that's how this method called cubitization works. So to conclude, I guess actually there's one other thing I should discuss, which is the order that you're truncating at. Basically, the cost of this, it turns out to be, is essentially just the order that you truncate this Jacobi-Unger expansion out at. And this one over here is super awesome. The reason why it's super awesome is because it actually saturates the lower bound on quantum simulation. It scales linearly with the evolution time, and it scales additively with this part over here, which exactly matches the lower bounds that we know for quantum simulation. So this is fantastic, and from a theoretical perspective, it seems like at first glance, it should be what you always do for simulation. And so this leads to my final slide, which is why are we still talking about things? Because we've got the optimal solution, but it turns out that actually sometimes optimal isn't optimal. One of the challenges with the cubitization approach is that there's no natural way to simulate time dependence. So if you've got a time-dependent Hamiltonian, it doesn't actually naturally fit into that framework without putting a clock register and exponentially large Hamiltonians, and it's just a pain, and nobody's figured a good way of making it work efficiently. And that rules out doing things like the interaction picture simulation that I was talking about. So that's a big deficiency that we have at the moment in our simulation methods. The other thing that's actually quite interesting, and this is a figure taken from a paper that Andrew did with Jan Su, Maslov, and some other people. But basically, what happened out of this is these PFs over here, these are Trotter formulas at the top, and bounds that they end up getting from it, versus the empirical results that they end up seeing down here. And again, one of the things that's interesting is that quantum signal processing, which basically is equivalent to the method that I showed previously, you'd expect that would be the best asymptotically, but in practice, it looks like Trotter formulas often end up beating it. And there's a lot of questions about why. Why do Trotter formulas end up beating this? Well, we know that there's this asymmetry because commutators end up coming in, but getting a good intuition for how exactly those commutators are providing these advantages is challenging. Furthermore, getting expressions for high order Trotter formulas that involve commutators for the error bounds is exceedingly hard. And it would be great if we could figure out ways of extracting that information to figure out how good are higher order variants. You know, if the fourth order formula does this well, what about the sixth? What about the eighth? So on and so forth. We don't really have a good idea because Trotter formulas are hard to take a look at. Similarly, one of the things that, and this also leads into Ryan's talk later on, is that while I've talked entirely about simulation in the abstract, there's a lot that's left to be done in the particular, such as how do we come up with the best circuits for simulating important problems like quantum chemistry? Other work that people like Robin and Jung Wong have done have looked at simulating particular problems of local interactions. And these models actually can be substantially easier to simulate than you might naively think when you take a look at these results. So there's a lot of work left to be done in applying these ideas in precise and creative ways to actual problems that we're interested in seeing. And then finally, there's this question that I think still needs some investigation, which is, well, all of this is talking about closed system dynamics. Well, there's been some great progress in simulating open quantum systems in the form of Lindbladian simulation methods. There's a lot that needs to be done. You can't just hand somebody a set of arbitrary Krauss operators, for example, and ask, what's the complexity of this? And I really think that quantum simulation should get to the point where we can address questions like that. Questions like, what is the complexity of simulating the standard model? There are many things that we just don't know about simulation, and I'm hoping that, well, within the next few years, and hopefully by bringing more people into the field with diverse perspectives, that we can get answers to them. Thank you very much.
So you write here that the three most prominent methods are Trotter, truncated Taylor series, and cubitization. But I'm curious, are there actually any situations in which the Taylor series method would be better than cubitization? It seems like it has sort of all the flaws of cubitization, but it's strictly worse.
Yeah, and that was sort of my take on it for a while. I was kind of bummed because I spent, we both spent a long time looking at truncated Taylor series, and it didn't seem to be performing all that well, which is why I'm super pumped about the interaction frame thing, because of the fact that in order to get the advantages for simulating diagonally dominant Hamiltonians using a technique, you've got to go to time-dependent simulation. And that's one of the things that truncated Taylor does a great job at. It's awesome for time-dependent simulations.
Okay, so you're including like the Dyson series as like a subset of the Taylor series.
Yeah. It should be a truncated Dyson series more formally, but yes.
Computer science related question. So you have all the theory that says for Turner Suzuki you can bound the error depending on the quantities. Now when you start compiling the actual subcircuits, then you do randomized compilation, also you randomize the error for the particular subcircuits. Is there any work or theory that looks at mitigating between these two ends of the spectrum?
So when it comes to the use of, say, randomized compiling as a particular example, from my perspective, the main application of that really is to end up decreasing the amount of unitarity in your errors if you care about what the gap is between the bounds that you end up getting for the diamond norm difference and what you get from randomized benchmarking. There's been some discussion about this, but I think that the two communities at the moment who care about these sorts of issues are a little disparate right now. But the use of either randomized compiling, or if you feel like going back to the 70s in the NMR literature, just dynamical decoupling, that I think is probably going to be a tool that we'll want to use in general. But specifying it for simulation, I don't think anybody's looked at it.
My point is when you compile the circuits, you also introduce some error in the part, so you approximate whatever the term was in the science.
Oh, that's what you mean. I'm sorry.
Randomized compilation was a technique particular technique that gives you some reasoning about the error on the hardware side. So is there any work that tries to mitigate It's between another approximation on the hardware.
Yeah, I mean, there are different ways that you can end up doing it. One way that you can end up doing it is on the outer inference loop, for example. Say you're running phase estimation. By using more advanced phase estimation techniques, what you can do is you can take advantage of the fact that you know that there's noise in the system and learn the quantities that you want you learn a small signal out of a lot of noise. Other approaches that tend to work better for situations where you've got a lot of noise is you want to have as low depth of a circuit as you possibly can. And for these, techniques like variational quantum eigensolvers have some element of robustness to these sorts of problems, but they also have challenges about large numbers of measurements and high variances that can sometimes also be an issue. So there's no free lunch, but there are definitely things that you can do outside of what I've mentioned here to deal with it.
You mentioned the specific problem of simulating quantum chemistry. What do you mean by the specific problem? I mean, what's the difference between that and simulating many-body quantum physics?
Sure. Really none. Basically, the problem of simulating quantum chemistry is really just you're simulating a many-body fermionic system. So it really, the Hamiltonian often looks identical to what you're looking at in electronic structure in particular. But it depends on the system that you're looking at. From my perspective, many-body physics is more general than solving some electronic structure problem with fermions. So, but you can see this all as kind of under the same umbrella. The techniques look very, very similar at the end of the day.
Yeah, I was trying to understand in what sense is it more general, in the sense that it's not. I mean, what makes the quantum chemistry problem more specific?
Well, the thing is that quantum chemistry, I mean, the only thing that makes it, I guess, more specific is the form of how the individual coefficients for the creation and annihilation operators in the description of your Hamiltonian where they end up arising from. So that's, from my perspective, the only difference between that and other applications in electronic structure. Some of these problems will have quadratically fewer terms, though. That's one of the big things. Like if you're looking at something like a Hubbard model, for example, or if you're interested in some materials problem that you're analyzing in like a plane wave basis, then the form of the Hamiltonian can be substantially simpler. But yeah, so I see it as specialization, but from the perspective of this talk, they're all instantiations of the same global idea.
Did you not say something about the question of the initial state? That this arose as an issue in chemistry?
Yeah, so the question about the initial state is, I should mention that that's actually from the perspective of simulation, that's one of the biggest open questions in general. If, say, we want to solve some problem like ground state estimation, like the previous talk was discussing, in order to be able to do that, we need to prepare a surrogate ground state for the system. And we don't know the complexity of preparing a ground state that has high overlap with the actual physical ground state. So that's one of the reasons why I intentionally spent very little time talking about this, because formally, I don't really know what to say about the complexity of preparing ground states, other than the fact that, in general, it's for many body problems, it's QMA hard.
So I just have a question about the ground states. Is there any real reason to care about ground states if they have very high complexity to prepare? Because it seems like nature just won't access them.
Yeah, sure. I'm sure Scott empathizes with that argument over there. But I think that there is reason, because if nature can actually find its way into these ground states, then that would be a profoundly interesting realization. Because I'm not fully convinced, although I'd like to believe that I'm not fully convinced by the quantum Church-Turing thesis. It is conceivable that there could be physics that exists in nature, which may give the world greater computational power than a quantum computer. So that would be profoundly interesting if it were the case. But of course, no counterexample has been seen so far. So
this may also simulate in a different basis. There may be a different encoding. So,
but if you don't believe in that, then you don't believe in Hamiltonian evolution, because the Hamiltonian evolution underlies the.
Well, all right. Let me be clear. I don't believe in physics. No, I'm serious. Yes. I'm 100% serious. I do not believe in physics. what I believe is that over the centuries, we've developed exceptionally good models for describing some things that we care about in the world. I do not believe an electron goes around and stores in some register a description of its quantum state that it updates with a pencil and paper in order to figure out how it evolves. These are models that we've learned. And they are just that. There is nothing deeper. They're extremely good models. But I don't believe in the reality of physics, personally. I don't think we have to. All we need to do is be able to simulate the mathematical models that are useful for us to describe the things we see around us. It doesn't have to be true, it doesn't have to be right, it just has to be useful.
In that spirit, another argument you could make for ground states is to say, well, who cares about, just simulating what nature does? Why not tell nature what it should be doing?
To some extent, there was a lot of work that was done in the past in, laser chemistry and things like this that was kind of telling nature what to do from that perspective. But yeah.
Okay, well, maybe on that note, we should take a break. We'll come back.